Attention! Attention! Hold on a second, because there's something here that just won't let me rest. Why is it that when you jump from a boat toward the shore with all your might, the boat indignantly glides away in the opposite direction, while you most likely end up splashing into the water? Welcome to my lab, my dear young Titan. Push that pile of unstable isotopes off the chair and hop on. I am Professor Zapnik. You know, the man who once tried to invent magnetic roller skates, but ended up stuck to the fridge door for 2 days. But no matter. Science requires sacrifices. We have already covered inertia, first law, and why it's harder to move an elephant than a kitten, second law. If you missed those videos, go catch up quickly, because Newton's laws are like a good TV series. If you missed the beginning, you'll just be staring blankly at the screen. The answer to the boat mystery above lies in Newton's third law, which physicists call the principle of action and reaction. Up until now, we've talked about force as if it were a lonely thing handed out by someone. But the reality is that force is never a solitary phenomenon. It is an interaction. That is the most important word today. When two objects meet, it's not just one doing something to the other, they both act on each other. Sir Isaac Newton summarized this by saying that if object A exerts a force on object B, then object B exerts an exactly equal but opposite force on object A. To understand this better, imagine putting on roller skates. I hope you're better at it than I am, and don't end up in the hedge. Stand facing a wall and push yourself off. What happens? You roll backward. But wait a minute. You push the wall, not yourself. So why are you moving? Because the moment your hand exerted a force on the wall, obeying the laws of physics, pushed you back. The formula is dead simple. The force exerted by object A on object B is equal to the opposite of the force exerted by object B on object A. This relationship is the apple of my professional eye. It says that the two forces are equal in magnitude, but their directions are opposite. This is exactly how we are able to move at all. When you walk, you push the ground backward with the sole of your foot. And the earth, since it doesn't want to be pushed back, and because it's quite heavy to move, pushes you forward. Essentially, with every step, you are using Newton's law to avoid staying in one place. However, many people fall into a trap here that even my smartest students stumble into sometimes. They ask, "But, Professor, if these two forces are equal and opposite, why don't they just cancel each other out? Why does anything move in the universe at all?" Well, hold on tight. It's because the two forces act on two different objects. Think of a slap. Only figuratively, please. If you hit a punching bag, one force acts on the bag. That's what makes it swing. The other force, however, acts on your hand. That's why you feel the impact or the pain. Since the forces aren't tugging the same object in two directions, they cannot nullify each other. This law also explains one of the greatest wonders of the modern age: rocket science. Many people think a rocket goes up because the gases push against the ground. But that's not true! It works in a vacuum, in the middle of nowhere, too. The rocket ejects gas molecules backward at high speed, action, and the gas molecules, in return, push the rocket forward, reaction. This thrust, this reactive force, is what takes us to the moon. Do you see it now? Without Newton's third law, the universe would be a boring, motionless place. We wouldn't be able to swim, since we push the water backward to move forward. Birds wouldn't be able to fly, and you couldn't even throw a simple ball without this law stepping into gear. That's all that fits into the basket of science for today. I hope you can now see the invisible dance of forces all around you. As for me, I'm going to try and peel myself off this magnetic wall. Stay curious, experiment a lot, and never forget, physics is with you. Bye for now. Until the next experiment, Professor Zapnik, signing off.